A 24-year-old graduate student walks into a room filled with the greatest scientific minds of the 20th century, Nobel laureates, the architects of quantum mechanics, space, men who had reshaped humanity's understanding of the universe itself. And within months, this young man would develop calculation methods so practical, so brilliantly simple, that they would help determine whether an atomic bomb would fizzle or devastate an entire city. His name was Richard Feynman, and his secret weapon was not superior mathematics. It was not access to better data. It was something far more powerful. He could see what others could only calculate. This is the story of how a young physicist developed an entirely new way of thinking about nuclear chain reactions. A method built not on memorizing formulas, but on genuinely understanding what neutrons actually do when they collide with uranium atoms. A method so effective that it helped prevent catastrophic accidents, predicted bomb yields with startling accuracy, and ultimately saved lives. But here is what makes this story truly remarkable. The techniques Feynman developed at Los Alamos during World War II were not just useful for building weapons. They represented a fundamentally different approach to physics itself, an approach that would later revolutionize quantum electrodynamics, earn him a Nobel Prize, and change how we think about the subatomic world forever. It all started with a simple question that turned out to be anything but simple. How do you predict what happens when you bring enough uranium together to start a chain reaction? Let us set the scene. It is 1943. At once, the world is at war. In Germany, some of the most brilliant physicists on Earth are potentially working on an atomic bomb. The United States, desperate to beat them to this terrifying technology, has assembled its own team of scientific geniuses in a remote laboratory perched on a mesa in New Mexico. Los Alamos, a place that officially did not exist, a town with no name on any map, a collection of hastily constructed buildings where the fate of civilization was being decided by people scribbling equations on chalkboard. Among these titans of physics, Richard Feynman was practically a nobody. He had not yet finished his doctoral thesis. He was decades younger than most of his colleagues. Bethe, who would win a Nobel Prize for explaining how stars generate energy, was running the theoretical division. Robert Oppenheimer, the brilliant and tortured leader of the entire project, had personally selected the scientific team. And yet, somehow, this young man from far Rockaway, Queens, would become indispensable, not because he knew more physics than anyone else, but because he understood physics in a way that made impossible calculations suddenly possible. You see, the Manhattan Project faced a problem that no one had ever confronted before. They were trying to engineer a device that had never existed. They were trying to predict the behavior of matter under conditions that had never occurred on Earth. They were trying to do all of this with limited computational tools, under extreme time pressure, with the knowledge that failure could mean Nazi Germany getting the bomb first. The theoretical physicists at Los Alamos had to answer questions that sound deceptively simple. How much uranium do you need to sustain a chain reaction? How fast will the reaction proceed once it starts? How much energy will be released before the bomb blows itself apart? Get these calculations wrong, and the bomb might not work at all. Or worse, it might work in ways you did not anticipate. This is where Feynman's genius came into play. Not the genius of knowing more, but the genius of seeing more clearly. To understand what Feynman contributed, you first need to understand what a nuclear chain reaction actually is, and not in the vague hand-wavy way you might have learned in school. You need to understand it the way Feynman understood it, from the ground up, from the perspective of individual neutrons bouncing around inside a piece of uranium. Imagine a single neutron. This tiny particle, with no electric charge, can pass through matter like a ghost walking through walls. Electrons do not stop it. Protons do not repel it. It just drifts along until it happens to collide directly with an atomic nucleus. Now, most of the time, nothing particularly interesting happens. The neutron bounces off, changes direction, keeps going. But occasionally, when a neutron hits the nucleus of a uranium-235 atom at just the right speed, something remarkable occurs. The uranium nucleus absorbs the neutron. For a brief instant, it becomes uranium-236, and uranium-236 is unstable, deeply unstable. The nucleus wobbles, stretches, and then tears itself apart in a process called fission. Here is the crucial part. When that nucleus splits, it does not just release energy, it also releases more neutrons, typically 2 or 3 of them. Each of these new neutrons can then go on to split another uranium nucleus, releasing still more neutrons, which splits still more nuclei. This is the chain reaction. 1 becomes 2, 2 becomes 4, 4 becomes 8. In a matter of microseconds, you can go from a single fission event to billions upon billions of atoms, splitting simultaneously, releasing more energy than humanity had ever unleashed in a single instant. But here is where it gets complicated. Not every neutron successfully splits another atom. Some neutrons escape from the surface of the uranium before they can cause another fission. Some get absorbed by impurities in the material. Some hit uranium-238, which absorbs neutrons without splitting. Some collide with nuclei and bounce away at angles that send them uselessly out of the bomb. The critical question, the question that consumed the theoretical physicists at Los Alamos, was this: under what conditions do you get more neutrons in each generation than you lose? When does the reaction sustain itself and grow? When does it fizzle out? This is what critical mass means. Not some fixed number written in a textbook, ideas, but a dynamic balance between neutrons being created and neutrons being lost. Get above that balance point, and the reaction multiplies explosively. Stay below it, and nothing happens. Now you might think this is a straightforward calculation. Count the neutrons, track their paths, add up the probabilities. But reality is far more complex than that simple description suggests. The problem Feynman and his colleagues faced was that neutrons do not behave predictably. Each one follows its own random path through the uranium. Some travel far before hitting anything. Some get absorbed almost immediately. The speed of the neutron matters enormously, because slow neutrons are far more likely to cause fission than fast ones. Stop. Think about that for a moment. The neutrons released by fission are fast, very fast. They are moving at roughly 10 million meters per second. At these speeds, they are actually less effective at causing more fission. They tend to bounce off uranium nuclei rather than being absorbed. But if something slows those neutrons down, if they lose energy through collisions with lighter atoms, they become dramatically more dangerous. A slow neutron is hundreds of times more likely to cause fission than a fast one. This is why water is so dangerous around enriched uranium. Water contains hydrogen, and when a fast neutron collides with a hydrogen atom, it transfers much of its energy. The neutron slows down, and suddenly material that was perfectly safe becomes potentially explosive. Feynman grasped this intuitively, not as a formula to be memorized, but as a physical reality to be visualized. He could picture the neutrons bouncing around, slowing down in water, speeding up when they scattered off heavy nuclei. He could see in his mind's eye how the geometry of the uranium mattered, how neutrons near the surface were more likely to escape than neutrons deep inside. This ability to visualize, to build mental models that captured the essential physics while discarding unnecessary complications, became Feynman's trademark approach, and it was exactly what Los Alamos needed. The theoretical division was facing calculations of staggering complexity. The differential equations describing neutron diffusion through matter were well known. But actually, solving them for realistic geometries, with realistic materials, under realistic conditions, that required either enormous computational resources they did not have, or clever approximation methods that nobody had yet invented. Feynman invented them. Working alongside Hans Bethe, Feynman developed what became known as the Bethe-Feynman formula. This was a way to estimate, with reasonable accuracy, how much energy an atomic bomb would release before the expanding core blew itself apart. Think about the challenge here. An atomic bomb is not a controlled reaction. The whole point is that it happens faster than the material can respond. Fission begins. Energy is released. The uranium heats up. It starts to expand. As it expands, the density decreases. At some point, The density drops enough that neutrons start escaping faster than new ones are created. The chain reaction stops. All of this happens in less than a microsecond. Thus, 1,000,000 times faster than the blink of an eye. The Bethe-Feynman formula captured this explosive dynamics in a form that could actually be calculated. It treated the bomb core as an adiabatically expanding gas, which means a gas that expands so quickly there is no time for heat to flow in or out. It related the outward acceleration of the expanding material to the rate of the chain reaction. It provided what physicists call a bottom line calculation. How hot? How fast? How much yield? This was not exact. Feynman himself emphasized that his methods sacrificed accuracy for speed and simplicity. But they were good enough. Good enough to guide the design. Good enough to tell the engineers what they needed to know. But Feynman's contributions went far beyond theoretical formulas. But in April 1944, Robert Oppenheimer gave him a new assignment. One that would test not just his physics knowledge, but his ability to communicate, to teach, to make others understand. There was a crisis brewing at Oak Ridge, Tennessee. Oak Ridge was the site where uranium was being enriched. Massive industrial facilities were separating the rare uranium-235 from the common uranium-238. Thousands of workers were handling radioactive materials every day, and almost none of them understood the physics of what they were doing. But the Army, obsessed with secrecy and compartmentalization, had deliberately kept the workers ignorant. They knew they were handling something important. They knew it was related to the war effort, but they did not know they were handling material that could, under the wrong circumstances, kill them. Emilio Segre, a physicist who had visited Oak Ridge, came back to Los Alamos, horrified. He had watched workers casually wheeling around large bottles of uranium nitrate solution, green liquid in glass carboys, handled like any ordinary industrial chemical. What the Army had failed to realize was that the safety limits they had calculated were based on dry uranium, pure solid material with no moderator present. But uranium nitrate is dissolved in water, and water, as we discussed earlier, slows down neutrons. It makes them enormously more effective at causing fission. The critical mass for uranium-235 in water solution is roughly 1/100th of what it is for dry material. 1/100th. A material that would be perfectly safe on a dry shelf could go critical if you dissolved it and put it in the wrong-shaped container. Workers could inadvertently trigger a chain reaction, a criticality accident, just by combining two individually safe batches. This was not a theoretical concern. This was a potential catastrophe waiting to happen. Oppenheimer sent Feynman to Oak Ridge as a safety supervisor. The young physicist was suddenly responsible for analyzing the entire plant, identifying every possible danger, and developing guidelines that would prevent disaster. And here is where Feynman's approach truly shone. The Army wanted him to simply give the workers rules. Do this. Do this. Do not do that. Put cadmium absorbers here. Keep batches separated by this much distance. Follow the procedures, and do not ask questions. Feynman refused. He later described the confrontation with characteristic directness. A lieutenant told him that the colonel had ordered him not to explain how neutrons work. Just tell them what to do to keep it safe. Feynman's response was essentially this: that is impossible. You cannot expect people to follow safety rules if they do not understand why the rules exist. They will inevitably encounter situations the rules do not cover. They will make judgment calls, and without understanding, those judgment calls will sometimes be catastrophically wrong. Los Alamos cannot accept the responsibility for the safety of the Oak Ridge plant, Feynman declared, unless the workers are fully informed about how the physics actually work. He won the argument. The colonel relented, and Feynman spent the next several hours teaching Oak Ridge engineers and managers about neutrons. He explained how neutrons are released in fission, how they slow down in water, how cadmium absorbs them, how the geometry of storage containers affects whether neutrons escape or stay trapped. All the concepts that were elementary knowledge at Los Alamos, but had been kept secret from the very people who most needed to know them. According to his own account, they thought he was a tremendous genius, not because he knew anything particularly advanced, but because he could explain it. He could make the invisible world of neutrons real and tangible and understandable. A few people, long afterward, thought he had saved lives. What made Feynman's approach so effective? Why could he solve problems that stumped others? Why could he communicate ideas that others struggled to express? Part of the answer lies in his absolute insistence on understanding, rather than memorizing. Feynman had a deep distrust of formulas that he had not derived himself, of procedures that he did not understand from first principles. There is a famous anecdote about Feynman and mental calculation. At Los Alamos, he noticed that Hans Bethe could square numbers near 50 almost instantaneously. How is 47 squared calculated so quickly? Bethe explained his trick. If the number is 3 below 50, the answer is 3 below 2500, and then you add the square of the residual. So, 47 squared is 2200 plus 9, which equals 2209. Feynman did not just learn this trick. He absorbed it. He understood why it worked, and then he extended it, modified it, made it his own. This is how he approached all of physics, never accepting a result on authority, always rebuilding understanding from the ground up. This same approach characterized his work on nuclear criticality. Rather than relying solely on complex diffusion equations, Feynman developed what historians of science have called visualizable methods. He created ways to picture what was happening to neutrons, to estimate answers quickly, to check results against physical intuition. For example, when calculating safe storage arrangements for uranium, Feynman invented a practical method that let engineers make conservative approximations on the spot. No need to run lengthy computations. No need to consult detailed tables. Just a simple procedure that captured the essential physics and gave a safe answer. His correspondence with Oak Ridge engineers during the war dealt with an astonishing range of practical concern. Floods, fires, wooden walls, gunk storage tanks, whether specific containers needed cadmium coating or not. All of it analyzed through his characteristic combination of rigorous physics and practical simplification. One historian described Feynman's Los Alamos work as deeply enmeshed in the barely existing field of nuclear engineering. He was not just doing abstract physics. He was inventing the rules and methods that would keep people alive while handling the most dangerous materials ever created. And through all of this, Feynman was also contributing to the bomb design itself, working on neutron measurements to determine critical mass, helping with the water boiler reactor experiments that provided data on chain reactions, tackling the devilishly difficult calculations for Teller's hydride bomb proposal, which involved neutrons of varying energies. His practical bent, his insistence on getting to the bottom line, his ability to sacrifice unnecessary precision for useful approximation, all of this made him invaluable. The war demanded results. It demanded answers that engineers could use. Feynman delivered. Now, you might be thinking that this sounds like engineering, not physics. Just practical problem solving, not profound insight. But here is where Feynman's wartime work connects to something much deeper. The methods he developed at Los Alamos, the visualizable approaches, the modular reasoning, the approximate calculations that captured essential physics while discarding irrelevant complications, these became the foundation of his later revolutionary work. After the war, Feynman tackled quantum electrodynamics, the theory describing how light and matter interact. This was a theory plagued by infinities, by calculations that diverged to nonsensical answers. The greatest minds in physics had been struggling with this problem for years. Feynman's approach was characteristically unconventional. Rather than working from abstract field equations, he developed a pictorial method. Lines representing particles. When you're representing particles, vertices representing interactions. the famous Feynman diagrams that would become the universal language of particle physics. These diagrams were not just a notational convenience. They were a way of seeing. They let physicists visualize what was happening in a quantum interaction, estimate which processes were important, calculate results that had previously seemed impossibly complex. Sound familiar? The same skills that let Feynman see neutrons bouncing through uranium, that let him visualize criticality and develop quick approximation methods for Oak Ridge engineers. Those same skills revolutionized fundamental physics. There's a through line from Los Alamos to Stockholm, where Feynman received his Nobel Prize in 1965. The physicist who could picture nuclear chain reactions clearly enough to make practical safety calculations was the same physicist who could picture quantum processes clearly enough to invent an entirely new way of doing particle physics. This is perhaps the deepest lesson from Feynman's wartime work. Physics is not about memorizing formulas. It is not about grinding through calculations. It is about understanding what is actually happening, about building mental models that capture the essential truth while remaining simple enough to manipulate. The neutrons do not care about our mathematical notation. They simply do what the laws of physics compel them to do. The physicist's job is to understand those laws deeply enough to predict what will happen. And sometimes, that understanding comes not from more sophisticated mathematics, but from clearer thinking. Let us step back and appreciate what Richard Feynman accomplished at Los Alamos. Do you want to learn? He arrived as a graduate student, barely finished with his thesis. Within months, he was developing calculation methods used by the most elite theoretical physics division in history. He was sent to Oak Ridge on Oppenheimer's authority to solve a safety crisis that threatened the entire uranium enrichment program. He invented practical techniques for nuclear engineering, a field that essentially did not exist before he helped create it. And through it all, he maintained his characteristic insistence on genuine understanding over superficial competence. The story of Feynman at Los Alamos is often told through his famous anecdotes. The safe cracking, the pranks on the sensors, Monsieur de Punide Shentaf, the bongo drums, and the irreverence. And those stories are true and delightful, but they can obscure the deeper truth. Feynman was at Los Alamos because he was extraordinarily good at physics. Not good at politics. Not good at self-promotion. Good at actually understanding how nature works and using that understanding to solve real problems. When Oak Ridge workers were in danger, Feynman did not just hand them rules to follow. He taught them physics. He made them understand, because he knew that genuine understanding is more powerful than any procedure manual. Understanding lets you handle situations nobody anticipated. Understanding lets you make good decisions when the rules run out. This same philosophy runs through all of Feynman's later work. His legendary lectures at Caltech were not about transferring information into student brains. They were about building understanding, concept by concept, from the ground up. His popular books were not dumbed-down physics for the masses. They were invitations to think the way a physicist thinks. The secret weapon Feynman brought to Los Alamos was not a formula or a technique. It was a way of engaging with nature, a commitment to seeing clearly rather than calculating blindly, a refusal to accept any result that he did not genuinely understand. And that weapon turned out to be applicable far beyond nuclear chain reactions. Here is what strikes me most deeply about this story. The Manhattan Project assembled the greatest concentration of scientific talent in human history. Future Nobel laureates everywhere you looked. Minds that had already transformed our understanding of quantum mechanics, nuclear physics, cosmology, debt. And yet, when it came to practical problem solving, when it came to making the abstract concrete and the dangerous safe, they repeatedly turned to a young man who had not yet even finished his PhD. What did Feynman have that others lacked? I think the answer is a kind of humility before nature. Not humility about his own abilities. Anyone who knew Feynman knows he was not short on confidence, but humility about what physics is for. Feynman never forgot that the equations are not the physics. The equations are a map. The territory is the actual behavior of neutrons, photons, electrons, the countless particles dancing their quantum dance throughout the universe. Too many physicists fall in love with the map. They manipulate symbols. They prove theorems. They lose sight of the territory the map is supposed to represent. Feynman never made that mistake. When he calculated how neutrons diffuse through uranium, he was picturing actual neutrons. When he developed safety guidelines for Oak Ridge, he was thinking about actual workers and actual barrels, and what would actually happen if procedures were violated. This groundedness, this connection to physical reality, is what made his approximations good. He knew which details mattered and which could be safely ignored. He knew because he understood what was actually happening, not just what the equations said. And here's the beautiful thing. This same approach is available to all of us, not just to certified geniuses, not just to people with advanced degrees. Anyone who is willing to insist on genuine understanding, to refuse to accept explanations that do not actually explain, to build mental models and test them against reality, can think the way Feynman thought. Physics is not a spectator sport. It is not a collection of facts to memorize. It is a way of engaging with the universe, of asking questions and demanding honest answers, of building understanding piece by piece, until you can see what others only calculate. That is what Feynman did at Los Alamos. That is what he did throughout his remarkable career. And that is what he invites all of us to do whenever we wonder how things work. The neutrons are still bouncing. The chain reactions still proceed according to the laws he helped illuminate. And the invitation to understand, genuinely understand, remains open to anyone curious enough to accept it. The universe does not hide its secrets. It simply waits for someone willing to look clearly. Feynman looked, and he saw. Perhaps you will too. Final visual. Closing contemplation on Feynman's Los Alamos legacy. An invitation to understand.